The third approximation for the derivative is centered difference, and for that we simply subtract the forward and backward between each other. So basically we have the forward difference and backward difference formulations. Forward difference minus backward difference. We already have those equations defined earlier in the previous slides. So this is equivalent to actually, and if we do this, it's basically the forward was fxi plus 1. Actually not the difference, but the Taylor series, let's say. So here first forward Taylor minus backward Taylor. And the difference is like this, xi, and from the series part, it is actually for xi plus 1, fxi plus f prime xi h plus goes like this, minus the backward difference, fxi minus f prime xi h plus goes this way. If you remember, it was changing the sign from plus to minus to plus. That's why I put a minus over here. So because it's a difference, we can simply see that, for example, the first term is cancelling out with the first term of backward Taylor. Second terms becomes like 2 times f prime xi, and the third terms also are cancelling out, and etc. So by doing this, we will have over here the difference, and the difference can be, so we can move this to the other side and keep fxi plus 1. Actually, let's don't do this and keep this like as the difference, because we want to have the difference and isolate this fxi value. So simply we will have fxi plus 1 minus fxi minus 1 equivalent to 2 times f prime xi times h plus this keeps going for the odd numbers, and that means 2f derivative is 3 now, xi and the 3 factorial and h cube, and again odd numbers, f5 xi divided by 5 factorial and h5, because the others have positive sign and cancels out with the forward Taylor, and it goes this way. And isolating f xi, of course also I want to truncate after the first term up to here, truncate, and isolate fxi, which gives us, here there is the difference anyway, fxi plus 1 minus fxi minus 1 divided by 2h. So actually, if we don't truncate, it was going to like f3 prime xi divided by 6 is the 3 factorial h cube, etc. These are minus because we actually isolated the this value. To isolate this, we moved all of these up to the left side, and that's why they became minus. And we truncate now from here. Truncate, which gives us the first order center difference. And we can show this graphically again. Let's draw the graph here. Fx, x, and the function is like this. And this is xi minus 1. This is xi, and let's say this is xi plus 1. So for this one we need xi minus 1 and xi plus 1 to predict xi. So two information is needed. In the forward difference we only needed xi plus 1. In the backward difference we only needed xi minus 1. But for this case we need both of them. So that can be considered as a disadvantage because we need more information for this case. And these are the function values, fxi plus 1. And we want to predict the derivative of the xi, this one, at this point. And this is the true derivative, which is f prime xi. And we know that this is the fxi. Anyway, to approximate this, what we do is, we can see from the equation here, what we do is simply subtract the difference, or we are actually combining the first or the previous xi minus 1 value of the function value with the xi plus 1 function value linearly. If we truncate after the first term, it is linear. And with this slope of this linear part, this is 2h, because each of these are h step size, and this part, and the difference here is simply fxi plus 1 minus fxi. So the slope here gives us the approximation, which is, let's write this way, fxi tilde is equivalent to fxi plus 1 minus fxi divided by 2h. That's the slope. So here actually when we truncate, we will have, you can see here, when we truncate, by the way, also here I think I wrote it wrong, this is h square, these are h square Ch04. The reason is that we divide by 2h and we divide these two, there is actually 2h here, and it cancels out with 2 over here, and this is still 6, and this h is cancelling out with 3. This is 3, sorry, this is also 3, we didn't divide yet, this is also 3, but here in the isolated terms this is just 2 because we canceled one h out, and that's why we can see this truncated part. So these truncated terms are the truncation error, which is actually r, and you can see that this is in the order of h square. This is very important, h square, and this can also be shown like oh square actually, and h square, unlike the forward and backward difference. So this is the advantage of this method. Although we need two information as opposed to the backward and forward differences, here the the error is to the power 2, and for the backward and forward you know that where O is h only. So in the backward and forward there is a linear correlation with the step size and the error, while in the center difference it is second order error difference. That's why this is more accurate. That's why center difference is more accurate. Because, or we can say the reason again, halving the step size now quarters the error. So if you want to predict the derivative, first derivative, if you have the information of xi minus 1 and xi plus 1, we need the function values. If you know them, you can simply, it is recommended to use centered difference because it is more accurate. And you can try halving the step size for this to further reduce the error compared to the forward and backward. So that's the importance of using centered difference rather than these. But if you don't have the xi minus 1 function value, just have this xi plus 1, you have to use forward anyway. Or similarly, if you only have this value, you need to use backward. So these are the three different derivative estimation methods, and you can use them to find the first derivative of a function.